Good morning, everyone. Thank you you've got up on this early morning to see me. So look at this waveform, nice sampled waveform. What's the peak value of it? It's a rhetorical question, right? But, right, thinking about it in software terms, a simplistic explanation of the sample value would actually suggest that it's sample 3 at 0.7, yeah? That's what your software would give you. But you'd be wrong, all right? The peak value is actually 1. And if it mattered, sometimes it does, it occurs between the two samples at position 2.6. And there we have it, right? Your samples are lying to you. What's the actual error of your peak value? Well, it actually turns out to be 3 dB. Of course it does, because I carefully arranged this example so it was. And again, that's significant. I mean, a 3 dB error in setting a compressor gain is going to actually matter. Even worse, it's going to vary depending on the timing of the waveform and everything else. So, I mean, it could be 0 dB, it could be 3 dB. That's not a good look. So, and as I said, the time may also matter. Quite often it doesn't, but sometimes it might matter. So the other thing that happens, if we do nonlinear operations, here's an example. If we apply x squared to the number, which we might do if we're trying to find the RMS value or the mean square value of the waveform, it means parts of the waveform are missed. And if we look at that, we end up finding that we've missed out the zeros that arise after the squaring operation. And if we did the mean of that, it would tell us, oh, the mean of this signal is 1. The mean square value is 1, which it isn't. It's actually 0.5. Again, a 3 dB error. So in principle, we need to have at least double the sampling frequency to make that work. Again, the waveform actually matters. And finally, another little example. If we apply nonlinear operations to, say, the output of a Fourier transform to get the magnitude spectrum, again, parts of the waveform can be missed. And they're the bits between the samples, and we'll get incorrect magnitude responses. And I found this out when I was trying to do pitch detection in my first job back in 1980. It matters. You can actually lose the harmonics. And if you are looking for the harmonics, that's really a problem. So it can be significant when you're looking at the magnitude results of a Fourier transform. Again, if we have more samples and we can see the waveform between the samples, then and increase the resolution, we can actually recover that information. So samples are not the whole story. The actual waveform level may not be the sample value. That's one takeaway, absolutely immediate. Just because the sample says X, that's not the waveform. It's related to the waveform, but it's not the waveform. And the problem is Shannon-Nyquist theory is so pervasive that we forget, or maybe we're never told, that there are terms and conditions. There are always terms and conditions. So it assumes the signal's processed in a linear fashion. It really only applies to linear time invariant systems. So no time varying operations, so that's no adaptive filters, fixed filters, no nonlinear operations, and really time variation isn't covered either. So interpolation and decimation is sort of on the edge, pitch shifting, adaptive filtering. So we really have to sort of put that assumption. It's great if you're doing equalizers or reverberation. That's fine, fixed filters. But once we start doing most of the stuff that we find interesting, then we really have to alter our perception. So what I'm going to do in this talk is sort of talk about that. Why does this happen to sample signals? That's going to be the first bit, the sort of reasons why it happens. Then we're going to do an example, which is actually the peak detector example. where the difference between the analog and the sampled waveform actually matters. Then we're going to look at some solutions. We're going to look at oversampling as a solution because that's already used. Then something called quadratic interpolation as a solution, which is quick and dirty, but actually can be quite helpful. And finally, a bit more sophisticated, something called B-spline interpolation as a solution. The third one actually has a very interesting, might be quite useful for sample rate changing, but we'll cover that when I get to it. Right, so why does it happen? Well, we've got sampling time here. I'm sure we've all seen that. We have our input waveform, which I've shown as a filtered square wave. It's filtered to fs/2, and we've got samples happily sampling the waveform. And we have instantaneous sample points, which gives us that sampled representative waveform at discrete time intervals. If we look at it in the frequency domain, a comb of time samples basically becomes an infinite sum of sine waves. So we get a comb of carriers of frequency, discrete frequency points, and we can consider modulating the baseband signal into copies of itself all the way up to infinity as double sideband suppressed carrier signals. So we have an infinite number of replicants, and it's the presence of these infinite number of replicants is why we actually get samples. If you did the Fourier transform, and I'm not going to set it as an exercise of the sampled signal, you would find that it is actually an infinite series of replications of the baseband signal. All right, and that means because of the presence of those extra bits, it alters the effective amplitude of the samples we see. So that's why it happens. It happens because once we sample, we have an infinite number of aliases there. In the frequency domain, we can see that we need to have at least 2 times the bandwidth so that these replicants don't overlap each other. And we were taught that at university. It means if we have any overlap, we can't recover the original signal. But those aliases are still there even if there are gaps between them. But if they're overlapped, it's called aliasing. And I've got a little example. Here's a sweep. Oh, God. Okay, has it stopped? Sorry, I mean, no. The young people here will have heard it for longer than I had. And in fact, right, and in fact, very interestingly, I lose it on this side of the stereo. Someone does a pan off hard to the other side above a certain frequency as well. Okay, so that was a linear sweep. It should have gone all the way up, and it sounded like a linear sweep, right? So here's an aliased version. And that should have gone up, and then it should have come down again, yes? And that's what you heard there was the alias of the sweep coming down as the other one continued up. So they basically crossed over, and you may have heard a funny little bit of sort of nasty distortion halfway through where the two were really close together and were little beating a bit. Okay, so the bands overlap. We can't recover the original signal in that sort of space. And when we look at it in the time domain, what we find is we can have more than one possible sine wave fitting the samples. Now, normally we're told that that's what happens when you get alias and if things overlap. No, actually that happens all the time. You can always get an infinite number of possible sine waves that describe the samples, right? if we're looking at the full frequency range because of the presence of the aliases. And it's those, if you like, extra waveform possibilities, again, that are reducing the effective or changing the effective level of the samples. In fact, it's like those warnings about investments. Samples values may go down as well as up in terms of value, independent of the waveform, not independent, but depending on the waveform. Okay, we can also think about it in terms of the frequency domain. It's like having a little glass mirror, and we've got Alice walking into the mirror, and we actually have an alias copy of Alice coming back out of the mirror. So sine wave walks into a mirror and another one comes out, and you actually heard that. So, and if you're really into it, set up a pair of parallel mirrors. I'm sure Trump would think that was fantastic. And you'll see an infinite number of reflected copies of yourself backwards to infinity. So let's summarize that. Result of sampling. After sampling, we have an infinite frequency range in the real world and copies of our original signal from minus infinity to plus infinity, and that's all effectively collapsed. Our samples are representing all of that, and nominally between the frequency of plus or minus fs over 2, although more conventionally we think of it as 0 up to fs. Which is why the samples are not always what they seem. So that's the result of sampling. You can think of it as a toilet roll wrapped round and round and round and round with infinitely thin paper, so it always lines up. And it's true for the frequencies already present in the signal, but also if you generate extra frequencies via distortion, which is quite a popular effect, you will generate those frequencies also effectively become infinite if you're doing nonlinear operations on the sample. So what we need to do when we do our processing sometimes is to unwrap that toilet roll. So how do we do that? We need to reconstruct our waveform. And so I'm never mind. So what we need to do, the way we normally think of it is we low-pass filter it to remove those infinite aliases in the frequency domain. The baseband can be separated from the alias. That's nice to see conceptually, and you filter it with a perfect low-pass filter. But what does that actually mean in the time domain? Because we do most of our filtering in the time domain on sample signals. Yeah, this is just an example of it actually happening. And we get the original signal back because we've got the baseband back. But what does that look like in the time domain? So in the time domain, it's quite interesting because what we're effectively doing is replacing that perfect low-pass filter, is replacing every single sample value with a, okay, that's not me. Honest. Replaced all the point and every other point with the impulse response. Right, yeah, and so basically every single point, every single sample in our original sample waveform is replaced by this sin x over x impulse response, and that gives us a nice simple linear reconstruction capability signal, because when we look at it, it's got a very interesting property, sin x over x. It goes to 0 at every sample point other than the sample point 0. At sample point 0, it's 1, but everywhere else, it's 0. So when we add them together, everything's conveniently 0 and all gets up, all matches perfectly. In fact, it crosses 0 at all times, sample times where the sample time isn't 0. And it actually has the property of orthogonality as well. So if we actually correlated those two samples, what we'd find is we got 0 result out of it. So it really is a useful filter impulse response. And because it's orthogonal, we can actually see the sample values as coordinates. There's one little niggle though. This impulse response is infinitely long, which is a bit tricky fitting into any finite memory machine that you want an output in a finite amount of time, but we'll come back to that. So we can look at them as orthogonal signals. That's a sequence of samples. If we took a whole song with n samples, what we've got is a set of n coordinates in multidimensional space describing one point to rule them all, and in the darkness find them. It contains all the information of that signal. And if we can define that point and we can isolate that point, we can perfectly reconstruct the signal from that. So that's the power of sampling if we can do it right. But the problem, of course, is that we've got this infinite impulse response. Now, here's a simple example of where it all breaks down horribly. The analog peak detector. Sorry, I'm discovered my watch doesn't show me. Am I going too quickly? Have I suddenly, are we okay? My speed okay for everyone? Good, excellent, thank you. Sorry, I learned my lecturing style in a Pentecostal church. So I'm used to audience participation, so the occasional glory and hallelujah, I'm fine. All right. So here's one we use without thinking. By the way, I looked at the code and I thought, what language is that? And I think it must have been a really old one, because I don't think we've used for do for a very long time. So sometime after analogue, because it doesn't have begin, but probably before C. Okay. The analog peak detector can see the waveform the whole time, so it doesn't really have a problem. There are some circuit details which we won't even worry about, but basically analog peak detectors, if you design them right, can work fine. But a digital peak detector can only see the sample. It can't see the waveform, so all it can do is make a decision on the samples. And that can give us quite serious errors. So, all right, again, this is a torture example. This is a digital impulse response that's a sync, basically the fastest signal you can get in a low-pass filtered thing. So that's a band-limited impulse response. If it happens to be in phase with the samples, we don't have a problem. The impulse sample happens to sit in the middle of the impulse response, and we get what looks like a digital impulse response, all zeros with a 1. And our peak detector will give us the correct peak value, but shift it half a sample, and we get something that looks like this. We get 2 high values. Probably that piece of code I showed would pick the first one. The impulse is not sampled in the middle. There's going to be an error. And this is the worst case error. And what is it like? Well, actually, it can be pretty bad. It misestimates the peak by 3.9 dB. So it reads 3.9 dBs low. Again, if that's going into a compressor, that's going to be a problem, right? We're going to misset the compressor. So that's pretty bad. It also matters when we're doing D to A conversion. Okay, this still happens in consumer devices. It shouldn't, because we've had enough experience of this. But you've got your D to A converter. It can output X volts when you feed in maximum signal, digital signal level into it, and people will still set that to the supply rails. So D to A converter happily outputs X volts. You put it into the filter to reconstruct it, and the overshoot then promptly clips, and you get distortion. And I said you can hear it, and it still happens. It's about 1.5 dB thereabouts. I mean, it's an issue for PA systems, digital PA systems, because obviously actually allowing 1.5 dB headroom to cover that matters. Otherwise, you know, it's a bit embarrassing if you're, you know, your high-price artist suddenly clips at an unfortunate point during the concert. It's not really what you want to happen. So what we need to do is to estimate the analog waveform, right? One way of doing it is by increasing the sample rate. And the way we increase the sample rate is interpolation. And the easiest way to think about it, and this is a very simple example, we just upsample by 2. The first thing we do is we add some zeros into the signal at the sample points we want to increase. So we want to double the sample rate. We basically, in principle, put a 0 in between each of the samples we've already got. What we then need to do is to filter that signal to reconstruct the values for those samples, which we can do with a finite impulse response filter or even an infinite impulse response filter, although more commonly, for a variety of reasons, which we'll see in a minute, we tend to use FIR filters. If we put that in through an appropriate filter, we happily fill in the gaps because they're perfectly predictable because we've sampled our signal properly, right? How much oversampling do we need? Well, the loudness meter, which I'm sure some of you have used in or seen indoors or even programmed, I don't know. ITU, the standard specifies at least 4 times oversampling and actually gives you some filter coefficients for it. Now, interestingly enough, all right, there are a couple of issues with that. It does give you a reasonable estimate of the peak value of the signal. It's less than a dB error, but it's not 0 error, all right? So that's point number 1. It introduces a delay of 6 samples at the original sample rate. So at 40, it's specified for 48 kilohertz. So it introduces a 6 sample delay at 48 kilohertz, which isn't too bad, especially if you're just looking at a visual thing. But if you were using it, say, for a feedback compressor, that might be an issue. And of course, computationally, it takes about 48 multiply-adds per sample to implement. And that's using an efficient implementation where this is the classic way of doing it. You don't have to compute the filter for the 0 samples. So what you do is you feed the same sample into a block of filters, and each of those filters has a shifted version of the impulse response. So the first one has every, say for ITU, say we were implementing by a factor of L, the first filter would be sample coefficient 1, coefficient 5, et cetera, and then the next one would be the next set of coefficients to fill in the gaps and so on and so forth. So you essentially fill in the gaps and you do the minimum amount of computation. A little bit tricky to program, but computationally fairly efficient. And you'll get your L times interpolated out. But obviously, if you need to change the sample rate by a big amount, then you're going to have quite a bit of computation. And also hidden in that is the bigger your sample rate change, means you're effectively trying to implement a very low frequency filter. What that means in terms of length of filter is the filter has to be a certain length in time, in real time, to do the filtering. So your filter gets longer as well. It grows faster than just the interpolation or upwards order. It has to actually get longer because it has to be longer to do the reconstruction properly. So interpolating things is effective. It's a standard and established technique, but because of the infinite length of that sin x over x impulse response, we have this uncomfortable tension between accuracy and length of computation, which can feed into delay as well as computation, sorry, delay and computation. Sorry, just buffering there. One of the interesting, I've never seen this picture until I plotted it, is how fast does the amplitude of the sinc function actually decay with length? It actually does it quite slowly. Sort of 20 odd dB per decade, which when I think about it, that would make sense. But so if you want accuracy, you need quite long filters. So you have, as I said, this issue with delay and computation in tension with the accuracy that you want from your reconstruction. One uncomfortable thing that comes out of this, if we're thinking super high quality audio, is in principle, you can never properly reconstruct a sampled signal. Not because you can't theoretically, but because you can't practically. It would take too long to actually do, for the signal to get through the filter. You know, if you've got an infinitely long filter, then it's going to take an infinitely long amount of time to get through, irrespective of how many multi-processing GPU computations you're using. It's just literally you have to wait that length of time for it to get through the filter. So we've got this issue with delay and computation. A lot of the time we can deal with it and we just, you know, pay the cost of the computation. But sometimes we can't. So if we're trying to emulate a feedback compressor, like, you know, a lot of the classic compressors from the early days of audio were actually feedback-based compressors. And that meant they detected the amplitude of the output and fed that back to do the gain control of the input. Now, in analog circuitry, that's kind of instantaneous. But if we now have to derive the waveform via an interpolation filter so we can get an accurate level to control our gain thing, that's an extra delay. And that means the dynamics of that emulation are not going to be the same, which may or may not be noticeable. I mean, I honestly don't know. But, you know, I could imagine, well, it doesn't sound like the LA2 I have gathering dust in my garage. So you've got to really, you know, I'm going to put it to you, you might actually want to get a good, reliable peak detection faster than you could get via interpolation. So the other advantage of lower delay is you might have lower computation. So alternative one is to use something very simple, you know, trade off some extra computation for faster estimation of the peak. And quadratic interpolation, I've used this back in 1980 for my pitch detectors, uses 3 adjacent samples. We construct a parabola going through it. It's a very standard numerical methods technique. And we use those 3 points to calculate the peak position. Yes, it involves some multiplication and division. If we want the location, it involves a little bit more computation. But if you look at that lower equation, actually the computation for the peak is actually pretty straightforward. It's 1 multiply and 2 shifts down. So it's actually quite a quick thing to do. And that will give you a peak. And for frequencies sort of below fs over 4, it's pretty accurate. When you, if you do it on that torque to track impulse, it will still read low. Okay, if you try it out, it will still read low. Not as low as the worst case sample, but not as high as the best case sample. You kind of get an okay-ish thing in between. On the other hand, you know, let's be honest, not many of us put an impulse through our system. So it's not really a musical signal that's useful. Useful for testing, but not much else. So that's quadratic interpolation. Very simple to apply. Computationally, actually not that feasible. It's actually stable as well. It's not an unreasonable thing to do. And it's useful in the frequency domain. If you're doing stuff where you're trying to detect the peak of an amplitude spectrum or peaks in an amplitude spectrum, then quadratic interpolation is useful. If you're trying to find the peak in a Kepstrom output or the harmonics of a signal, it's something you can do. And here's a little trick I got from Julius, well, I'll say his name later. But you can use if you use a Gaussian window, it turns out that the log representation of the frequency domain is parabolic at the top. So you can actually get quite an accurate positional estimate of your harmonics pitch from between samples, which is kind of handy for a lot of applications. And I discovered, if you look at the difference between a Hamming window, the raised cosine window, and a Hamming window, which is sort of a raised cosine with a little step on it. The reason for that step is you can cancel out the first adjacent bins, which is very handy for pitch detection because you sort of get rid of the most interfering thing likely for you. You can play that trick with the Gaussian window because Gaussian window is infinitely long as well, so you have to chop off the ends somehow. If you actually add a 9% step to cancel the first bin, it actually works, and you still get the nice curve at the top. And doing that, all right. But there is one thing you do have to do because you need the magnitude, you have to square the Fourier spectrum. And you need at least 2 times oversampling to do that reliably. But for FFT computation, there's a really efficient way of doing that. And the efficient way of doing that, and here's a very simple example. It's not a great window, but a little triangular window. What you do is you add some zeros to it. And then do the Fourier transform. So if you double the number of zeros, you would get double the Fourier frequency resolution. You don't get any more information, but you effectively interpolate the curve a bit. And computationally, it's very cheap because you don't add that much extra computation to your FFT to do it. If you add even more samples, padded zeros, before you do the transform, you get better interpolation. The way it's shown there works for magnitude only. If you were worried about the phase, then you'd need to put the zeros symmetrically on either side of the window before you did your Fourier transform. But it's a quick and easy trick to do to get a better quadratic interpolation in the frequency domain for frequency peaks. And it was Julius Smith of CCRMA who came up with that idea. So parabolic interpolation of or quadratic interpolation of frequency peaks. Again, a fairly quick and accurate way of filling the gaps between the samples to get the true peak rather than the what the samples tell you. Okay, so that's method 1. So we've got interpolation we can use to fill in the gaps between the waveforms. We've got parabolic interpolation. There's one other thing I'd like to talk about, and that's something called B-spline interpolation. Okay, this was developed in the 90s, early 90s by Unser. And the idea here is use splines. Now, looking at my slides this morning, I realized I'd actually doubled the effective sample rate on my splines on the thing. 2 should be 1, 4 should be 2, and so on. So you form a family of B-splines, beta splines, by successively convolving a simple rectangle. So simple rectangle is our hold for one sample circuit. If we hold it for one sample, that's a B0 spline. B2 spline can involve two square waves together. You get a triangle wave, that's B-spline. You know, three together, it's some sort of quadratic thing. Sorry, two together, it's some sort of quadratic thing. Three together, it's a third order one, and so on and so forth. So very easy to generate, probably very easy to work out an equation to calculate for an arbitrary point. You'll notice something about these things, right? Do they extend off the graph? No, they're all sitting within the slide. There's no infinity and beyond on either direction. The advantage of B-splines is they have a finite length. They've got a X samples of support. So we've immediately got a predefined length of time we need. You know, we need that amount of time to form them in terms of working out the shape and working out the waveforms. So that's a really positive advantage that we can implement them with short filters or whatever. But there's a problem. They overlap. Unlike sin x over x, they don't go to zero at all the sample points. That means that whenever you change one, there's interaction that goes along, and you've got to calculate and work out those interactions. And that, certainly for 1991, immediately said, you've got to solve a set of simultaneous equations. Okay, now that's a problem. That's not really a problem these days. You know, I mean, a four variable simultaneous equation, you can probably do in the registers of a GPU on the fly. There's probably enough registers there just to do it. And it's done, all right? So these days, it's not such a hard thing to do. But you can't use them directly. They are more complicated to do. And usually, they require a matrix inversion per output point. Now, what Unser did, and this really, I think is a brilliant step forwards, is he worked out, we can do a filter rather than a matrix inversion. If we have a pre-filter, followed by our spline interpolation reconstruction thing, we can replace the matrix inversion by essentially this pre-filter, or what he called an analysis filter. And it's got a very simple, this is an example for a third order, it's got a very simple transfer function, you know, 6 over z plus 6 plus z to the minus 1. What's the problem? Anybody see what the problem is? The problem is we have to be precognitive. We need a crystal ball for it because we've got a one sample in the future undelay, whatever you want to call it. It's non-causal. So yeah, precognitive processing, anyone? Okay, what can we do about that? Well, obviously, if we're dealing with stuff in a DAW or stored data, we can just run the filter backwards from the end to the beginning. It's easy enough to do, just split it into 2 bits and, you know, run it backwards. But that's not very helpful for real-time processing, is it? So what Unser showed is you could actually make your filter by using 2 IIR filters, one running forwards across an impulse and one running backwards across the impulse. Now, you can do that offline and you get the impulse response for this filter. It's unfortunately infinitely long, like our sin x over x, and you might quite reasonably ask, oh, Jamie, you've just wasted 40-odd minutes of our time getting to this point. It's still infinite. Yes, it's still infinite, but unlike the sin x over x, which decays as 1 over x, these infinite impulse response filters decay as or exponential decay. So they get down to very low error levels quite quickly. So these filters can be comparatively short. And also, more importantly, if you're doing processing, you can do the pre-processing before all the nonlinear stuff where you need to know the waveform. So it's less of a problem than one realizes. And the real advantage is it potentially gives you exact reconstruction. So especially for things like sample rate changing, where you really do need to know the exact value of the signal in between the sample points to do the interpolation properly. So small pitch shifts, for example, that would be an example. But you can make a windowed version of that, which will end up being shorter than the equivalent sin x over x impulse response window for the same level of accuracy. Right, I need to move on a bit. Okay, this is what filters look like in the time domain. It's a bit wiggly. This is what they look like in the frequency domain, and you can see that the pre-filter's a bit peaky at the top end. But again, that's a dynamic range issue rather than a computation issue. And that just sort of shows the composite response, which is in black. Actually, it's pretty good. It's not that bad as a filter response. Certainly something we can make use of. And here's a little bit of an example. This is a degree 1, because I thought this is an easy one to say. So this is an example of a second degree first order spline rather than a 0th order spline. It's got linear variation between the center and the two adjacent samples. Obviously, if it's perfectly lined up with a sample, you use the sample value. That's what the 1 says. For a 2-tap, if it's slightly offset, we end up with 2 values of the spline that are non-zero. And we essentially form the middle sample by adding the appropriate weighted contributions of those 2 samples together. When you look at it in practice, it's linear interpolation. That's what it's giving us. It's determined by the spline. But if we do a 3rd order one, which takes 4 points, possibly 4 points, again, same deal. If it's not quite the same deal, if it's centered on a sample, we can't just pick the center sample. We actually have to add in a little bit of the 2 adjacent samples to form the actual original sample. Then as we slide it along, then there you can see we have to add a weighted summation of up to 4 samples, okay? Now, the thing is, we can pre-calculate that spline, either with an explicit equation or just by doing it brute force and making a great huge table for it, depending on how much memory we'll want to spend. So it's possible to get very fine divisions of our spline positions, and therefore we can actually get very accurate estimations of the waveform between samples. So, you know, this is a solution for working out what's between the samples. And if we look at the sort of errors you get, again, you really do have to end up being oversampled with respect to the individual signal bandwidth, but 2 times oversampling. So if you were running at 96 kilohertz sample rate, actually that would probably work fairly well. And you know, and that would be for signals sitting at 20 kilohertz. If we're looking at more realistic tone signals, which are going to be down in the 1 kilohertz, 4 kilohertz region, then the error will be even less. So, in conclusion, the ability to measure the audio waveforms level is important to many audio devices, and knowing the waveform matters for nonlinear operations, for sample rate changing, etc., etc. But the actual level may not be the sample level. It may be an intermediate level between the samples, and nonlinear operations end up not working as expected. Dynamic control using levels may also be affected. So various proposals have been proposed to describe to ameliorate this: upsampling, quadratic interpolation, or B-spline interpolation. They're all tools you can use, but the important thing to remember is the samples are not always what they seem. Any questions?